Hi, I'm Ben Miller, and welcome back to Life in the Fastlands. In today's episode, I get to show you more of my conversation with John and Charles, where we talked a bit more about protocol and Ethernet network testing, as well as forward error correction, which is an essential element to anything high-speed digital nowadays. So without further ado, let's get started. Now, Charles, can you tell us what protocol and network testing is and why it's so important for data centers?
Well, yeah, this is a very important part of getting to market, as they say. A lot of the network tests, what we call Ethernet network test or performance test products, use the Ethernet protocol, and we test at different layers. So, for example, we like to test at layer 3, which is a networking layer. And this allows us to test, for example, how do routers talk to each other using the networking inter-networking protocols like BGP or OSPF and many others. Um, and how do they perform on a global basis? Our test systems can test those things. So in other words, how do they maintain their links? How do they transport information from one place to another? And then there's the switches and the network equipment, the edge routers, which is the way that a data center talks to the outside world. And then there is a bunch of equipment, called servers and storage devices and network switches that make up what we call network infrastructure, the actual equipment that transports all the data that comes in from the external world into the data center and then eventually back out. And all of that equipment has to be tested not only as standalone devices. So, for example, the performance of a switch, 32 ports of 800 gig E or 32 ports of 400 gig or 64 ports of 100 gig E. How well does that switch work? Does it have full line rate Ethernet packet throughput at 100% line rate? Does it process all the packet sizes? Does it have proper latency, which means the delay of a traffic of packet from one place to another? And also, how efficient? Do we process all the Ethernet packets and the frames and the data in a way that when we're using, let's say, the Teams application, or if we're using our browser, or we're downloading a file, or we're sending a large email, do we wait 5 minutes for that? Well, all of that kind of performance has to be tested, and our tools can test that packet throughput. They test latency, delay. They test the accuracy of the packets. How many times do they have to be retransmitted? Or are they being transmitted and there's an error? And we test those types of things so that a company, a large network equipment manufacturer, or a large service provider, or a cloud data center, or a large enterprise, when they buy that equipment, they can know that they have an independent way to set up that piece of equipment, set it up in the way that it was designed to be used in the real world, and then have our testers simulate the real world. And when we simulate the real world network, we call that testing in order to simulate the production environment. And that's what our testers help customers do. So our tools help predict long-term reliability of a component. So we can make measurements like forward error correction performance, like something called frame loss ratio, like packet loss, latency measurements. We can determine over time and temperature, as an example, how well will this device do in a network? And if you put it in that network, will it be reliable and will it not drop packets? Will it not create errors? Will the networks just stop working? That's called a failover test. We do certain kinds of tests to actually simulate network ports in the network infrastructure actually going down, or a whole router going down. So there's certain things that we can do, and we can also measure the convergence. How fast does it come back together? In Ethernet, in the area of new technology, most of the testing is focused in the first year or two. Mostly, we're testing the reliability of the forward error correction used in Ethernet, the reliability of the device, that it can handle full line rate traffic, and that its bit error ratio, meaning the number of errored bits divided by the total number of bits that have been transmitted or received, can be calculated. And there are IEEE and OIF standards that John talked about that give us tolerances. and we can measure the device performance to the maximum tolerance. And if we're under that maximum tolerance, that means our interoperability, our ability to work with other network equipment built by different manufacturers, our ability to do interoperability is dramatically increased.
Let's talk a little bit about forward error correction, or FEC. Can you talk a little bit about what FEC is and why it's so important in Ethernet? And also, could you define what a FEC-aware solution is?
As you look at the chronology of specifications here, I was just doing a quick check here earlier today, going back to the BA specification, which was 25 gig per lane. Back in those days, we had relatively simplistic reference receivers, and we had no FEC. We had a native BER of 10 to the minus 12 BER, and things just kind of worked. And we harken back to those days as the good old days, because you would measure it, you could see it, and you could measure it on any given lane. Since then, we've progressively gotten more and more sophisticated reference receivers, and we're incorporating, well, as you go higher in speed and you have to combat these intrinsic channel loss behaviors, your BER has gone up. We're now operating with a native bit error ratio, or BER, of about 1 to the minus 4 BER and 1 to the minus 5, depending on which specifications you look at. That's far too high an error rate to build a functional data center around, to watch a video from, or to do any kind of commercial enterprise or cloud computing systems. It's very, very high error rate. And as a result of that, we've incorporated a Reed-Solomon basically forward error correction into the signal. We encode the data, we wrap it in some encoding. It gives us the ability to, number one, detect the error on the receiving side, and gives us good insights on how to correct that error. And now that's become a fundamental staple of every operating link these days. We rely on FEC at all of these higher speeds nowadays to get us an effective BER down to 10 to the minus 13 or lower, which is where you have to have it to have a functional system. So the testing of that gets a little bit complicated because FEC is frequently striped across multiple lanes in a link. So by looking at a single lane, you have some challenges in actually evaluating the signal you're looking at. There's a physical layer tool set that we provide that's associated with our BERTs, our M8040 or M8050 BERTs, that allows you to kind of fake it and do single lane by lane FEC analysis. And really it boils down to examining the proximity of the errors that happen natively when it goes across copper or an optical interface. If you have burst errors that are very close together, that's a very bad scenario, and you want to avoid that. If you have errors that are uniformly distributed over time, and you can have lots of errors as long as they're spread out, that's the kind of error condition that the forward error correction is very effective at correcting and operating with. So you want to measure that. And that's the frame loss ratio operation that Charles was talking about a moment ago. As you're testing an active optical cable or a system, we have infrastructure that allows you to utilize something such as a G800E, which Charles can talk more about, to broadcast full 8-lane traffic onto a module or a cable. And we can examine how close the design is to the limits of FEC. And there's a new concept known as the FEC tails, which is a term that I'm sure everyone will become more familiar with over the next couple of years. It doesn't really matter how good your part behaves. There are systems that are extremely close to the precipice of 15 consecutive errors, and it would actually have no FEC tail, to devices that have relatively good performance and have very short FEC tails. And being able to examine these FEC tails in effect is become a new physical layer measurement. Really, it's a protocol level measurement. It's above the typical physical layer that we work with, that it gives people insights as to how good their designs really are.
What are the key takeaways that you want our viewers to leave with today regarding the next generation of Ethernet standards?
I think the one thing that people need to expect here as we move into the next performance level is some changes to our traditional measurement science. Concepts that have traditionally supported us here over the years, last decades, eye height calculations, our standard jitter calculations, are starting to fall apart at these speeds. So I think we're going to see changes, and we'll see these proposals get teed up here at the Standards Committee. Some of them will be shot down, others will be brought in as the new way of doing things. So there's a lot of change in traditional measurement science right now. It's going to be important for people to track this stuff and to work with your measurement partners to make sure that you're using the latest techniques and techniques that are approved by the standards bodies.
So today we live with errors. In the past, we could make those links error-free, like John was saying earlier. Today, every link has error. The question is, what is the acceptable error for my application and for my interconnect or for my switch or for my router or my server? And this is where our tools come in and help the engineering teams, the architecture teams, the test engineers determine what they're going to do when they build that production network. Are they going to recommend the right components in the right configurations to be able to ensure a highly reliable network? Because that's what it takes to run this digital economy that we're all so tied into. Without this kind of performance, our quality of our lives and experiences using all of these applications and these things that we do and use in our everyday life would degrade significantly, which is staggering to think about. But this is why the standards, IEEE, OIF, are so important, and that the measurement tools that we create and Keysight brings to the market are critically important to basically underpin the foundation that makes these networks work. And so we help to build a solid foundation that someone who's investing hundreds of millions of dollars in network data centers can do so confidently.
Thank you again to Charles and John for their time and their expertise to help me make this video and making it a really great discussion. If you'd like to see more about Keysight's Ethernet solutions, please check out keysight.com/find/fastlanes. We'll point you to some other resources, and we have a ton of great information on keysight.com if you're doing any kind of development with these new Ethernet standards. And please feel free to reach out if you'd like to talk to one of these experts or any of the other experts that we have about our solutions. Otherwise, until next time, this has been Life in the Fast Lanes.